So tonight I'm just going to review and then we'll call it a night. The last exam covered up to the telescope and Doppler shift sections, but it didn't cover those carefully. So yeah, sorry, the shifting pages is not perfect, and actually I'm not sure why this is zoomed at all. So let's look at the Doppler shift. Now in their presentation, the last students that did the presentation talked about the Doppler shift, and I've talked about it very small amounts, but it is an important concept. So this equation here is the equation that tells you how big the recessional velocity is. Recessional velocity means velocity away from you. Remember, I told you Doppler shift can only measure velocity in the direction of line of sight. It can only measure if something's coming towards you or away from it. It doesn't measure if it's going tangentially. And so this here, the velocity that it's moving is the shift in wavelength. Lambda 0 is the wavelength in lab. And delta lambda is equal to the lambda that you measure minus the wavelength in lab. That's how we calculate the recessional velocity. Now you might recall from class I said we often define z is equal to the wavelength shift over that wavelength in the lab, and so then we can just write v sub r is equal to zc. But the important thing is you should be able to understand that. Understand what kind of shift means that something is moving toward you.
So red shift.
Blue shift. A blue shift means it's going toward you, but then that begs the question, what does it mean to say it's a blue shift? Okay, the frequency is getting higher or the wavelength is getting shorter, because blue is the short wavelength edge of the visible spectrum. Red is the long wavelength edge. If something's moving away from you, the wavelengths are going longer, so we say it has a red shift. So make sure you know that Doppler shift and how it works. Not the physics of how it works, but how it's interpreted. Big sigh of relief. Okay, the detecting of light for telescopes, it's important to keep in mind what's the most important aspect if you're going to buy a telescope for your home use?
The diameter of the
Bigger is better. The bigger the diameter, the more light it will collect, the fainter things you'll be able to see. Now you do want to make sure it has reasonably good optics, right? You don't want optics that your neighbor's 5-year-old ground. You need optics that are good, but assuming you have reasonably good optics, bigger size is always going to be better. So you have first this equation, collecting area is proportional to the diameter squared. It's proportional to the area. Area is pi times radius squared, or pi times diameter squared over 4. Also, you have better resolution, as you can see finer details when you have a bigger telescope. So we talked about different kinds of telescopes, visible telescopes, infrared, radio. Why would people want telescopes that are not visible light telescopes?
To detect other ones in space.
But why?
Because some things don't emit in the range that we see.
Okay, some things don't emit much in the range we see. They emit much more in other ranges. Also, it allows us things like being able to see with the radio telescope. You can see through clouds and you can see where there is cool hydrogen gas. So you can find different kinds of things that we tend to think are invisible because they're not visible to our eyes that are out there. So different wavelength ranges have different goals of what they try to look for. You might remember I showed you different images of infrared images, and you can see different details depending on what the range of wavelengths was. Now with the telescopes, the actual resolution is given by this equation. Remember I said bigger is better. D is the diameter, once again, of your telescope. Alpha is the smallest angle that you can resolve, the smallest detail you can see. What? You guys are all shaking your head.
He's being stupid. She's looking
I-
at me, I'm just saying keep your eyes.
Okay, so it's a very complicated interaction.
I'm trying to help you out, Professor.
Yeah.
Thank you. Thank you for that. And I'm going to choose to believe it. So having a bigger diameter means that the resolution angle alpha is smaller, and that's better. That means you can see smaller details. Now with telescopes, we talked about refractors and reflectors. Refractors use lenses that bend light. Reflectors use mirrors. Both of them will cause the light to focus, so both can be used to focus light. Which one is by far the dominant telescope used in astronomy research? Mirrors, the reflectors. Can you give me some reasons why reflectors are better? As compared to refractors. Well, we have to be more specific. You have different kinds of aberrations. Some can occur with both and some don't. For instance, chromatic aberration. That is, different colors have different focal lengths for a lens. With a mirror, all colors have the same focal length, so you just don't have that aberration, that distortion in the image. You have things like, well, the spherical shape is truly not the right shape, but they usually grind things to spherical shapes. You have spherical aberration. When you make a lens, you have to grind two surfaces. For a mirror, you only have one surface, so that's half as many surfaces to worry about. Supporting a mirror takes a lot because they're heavy. And mirrors can sag under their own weight. Or, excuse me, lens. Supporting a lens takes a lot because they're heavy, and lenses can sag under their own weight. The mirrors you can support on the back side. They tend to be light, and you can fully support them so they don't have that problem. One of the biggest things that I like to focus on is segmented mirrors. You can make mirrors with segments, and you can have those segments so that they will adjust to give you adaptive optics. Adaptive optics, you're actually changing the mirrors just a little bit to adjust for the atmosphere. Because when you look at a star and you see a twinkling star, the star itself is not getting brighter or dimmer or anything like that. It's the atmosphere that the light is going through is making the light go through different paths. And so it's going like this as far as our eyes can tell. And that's what's causing the twinkling. Adaptive optics can actually correct for that to hold it still, even though the atmosphere is making it look like it's bouncing around. Now, I don't have here the equations for the magnification of a telescope, so I'll write it down. The magnification of a telescope minus the focal length of the objective divided by the focal length of the eyepiece. You should know which one's the objective, which one's the eyepiece. The objective needs to have the long focal length to make a bigger magnification. The eyepiece is short focal length. The minus sign is there because a normal telescope has an inverted image, which kind of makes it hard when you're trying to track somebody. If it's in the top right corner, you need to move it to the left. Normally we'd say it's in the top right corner, I need to move it to the right to get it in the center. But no, you need to move it to the left. If you were using a telescope like that to watch like a football player, you would have all kinds of trouble. In the sky, we usually don't really tie the two together, so it's not as much of a problem. You had a question, Holly?
Wait, which is which?
What's what?
Which is which? You said FOF.
Oh, if you have a telescope, if your object is out here, then the lens that is closest to the object is the objective. And if your eye is back here, the lens closest to the eye is the eyepiece. So the names actually tell you where they're located as long as you connect the name of the lens with what it means. Okay, now I'm going to move forward. Oh, I did have the equation right there. Okay, now I'm going to move forward to the stuff that was originally scheduled. I think it was Ken had asked me, how much of the stuff are we covering from before what was scheduled on this exam because we didn't get to everything last exam. And so here we've got that, the stuff in the telescopes and the Doppler shift. So now new material. Now this here is a review I wrote based on a different textbook. So that means that, what was that? Okay, bring it back, hopefully. Okay, so this here doesn't have the same chapter names or units. It's more like normal size chapters instead of a unit that's really tiny that you do multiple units in a day. So we have the solar system. And this starts here with the Earth-Moon system. Well, we need to back up a little bit and talk about the solar system. You have one question that once again, that's going to be on the test. So, Chioni, what's the one question you know is going to be on the test?
One question I know is going to be the
Yes.
From there.
Okay, I take it you don't know. Kendrick raised his hand before you do. What's the one
planets? You need to know the order of the
Okay.
planets.
You need to know the planets in order from the sun out.
And which one have moons?
Well, not necessarily which ones have moons. You're going to need to know some aspect about them. So it could be something like, which ones are rocky and which ones are gassy. It could be which ones have moons and how many how many would be 0, 1, 2, or more than 2. That's as far as the numbers, you don't have to know 68 today, 69 yesterday, whatever. That would be the wrong direction. Or it could be which ones are icy. Or which ones are icy?
The father.
The last two, Uranus and Neptune. Right, so there will be something like, I could ask you about the densities. I could ask you about the gravities. Right, just something, and of course if I ask you about the gravities, it won't be knowing the numbers of the gravities. It'll be, which ones are higher, which ones are lower. If I ask you about the densities, it won't be knowing the densities. I know a lot of you learn, hey, Saturn got the lowest density, I won't ask you specific numbers. I'll do something like, above 2 or below 2. But you're going to have to know some additional aspect besides just the names of the planets. Now, since you have to know the names in the order, what are the names in order? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune.
And the planetesimal dwarf thing.
Pluto.
Yeah. Okay, how many dwarf planets do we have?
2.
Don't we have
For
3?
now.
5.
Listen to Ken. We have 5. What are their names?
2.
Pluto, Ceres, Eris.
Pluto, Ceres, Eris.
Don't know the other 2.
The other 2 are the Hawaiian ones. Make,
Make.
and Haumea? Something like that. So we have 5 dwarf planets. I'm not going to ask you to name the 5 dwarf planets. Question, Holly?
Is Plutoid also Pluto? Because in the book it said.
Plutoids are objects like Pluto.
Okay. So it said it's a T and know that it's also a dwarf planet.
Then that would just be Eris, Haumea, Makemake, and Pluto.
Make.
And there's Plutinos, there's neutrinos, there's trans-Neptunian objects. A lot of those, I get confused. And so I don't want to... Yeah. What?
I was making it as you joke about Pluto.
Oh, okay.
It wasn't worth repeating.
All right. So, talking about the solar system, how do we believe the solar system formed?
How do we what?
Believe the solar system formed.
Big Bang. Just go around.
Okay, we have a big cloud of gas. Shock wave hits it, starts condensing because of gravity, and then you get centers where more things condense. If it gets large enough, it becomes a star, the sun. We only had one of those that formed. Other things became planets, started as planetesimals, protoplanets, became planets by collecting material. Inside of the frost line, it was too hot for volatiles like water, methane, to condense. And so those were really not accessible, not available for the planets to collect. Hence, all of the planets inside the frost line didn't get very large because they couldn't grab onto the most abundant gases. What they could hold onto were things with high melting temperatures, the silicates, and iron. And so our planet, like the other rocky ones, those are the primary ingredients. And of course, now we have here things about the Earth and the Moon. There's far too much to go through all of the stuff on the Earth and Moon. And this being based on another chapter, we don't have things like the small angle formula wasn't something that came in here. The tide's certainly not something we covered here. But we have things like how the Earth is believed to have developed. In the stages of planet formation, after you've gone through, planetesimal, protoplanet, becoming a planet, you have the differentiation. One of your homework questions is about differentiation. What is differentiation?
Heavier or denser materials.
Yeah. When you have the planet in basically a gooey mess, more dense materials will sink and less dense materials will float. And so you end up with a separation. That's what the differentiation means. It's the separation of material, separated by density, so the most dense material is in the center. So since the Earth is largely silicates and iron, iron's more dense than the silicates, so the core is iron. And the silicates are on the outside. So we have mostly silicates out here. If we really wanted to get a lot of iron and we had some magical way, we could just pump it out of the core and we'd have a huge supply of iron. But it would require magic. Yes?
Okay, do we need to know, are we going to have to explain the process of how we believe the solar system was formed, in short answer? Or is it
You may have a question about, what was it before it was a solar system? So what was it before it was a solar system?
cloud of gas?
Cloud of gas. And then you'd have, so what happened to make it change from cloud of gas to the solar system? Shockwave. And then you would have, why did planets closer than the frost line grow this way and planets farther than the frost line grow that way? It would jump to that. You wouldn't have stuff in between. You could have questions about protoplanets and planetesimal. I would not ask you to differentiate between a protoplanet and planetesimal, just that those are early stages of planet formation, which actually the names mean. Planetesimal is a very tiny planet. Protoplanet is prototype of planet. So the names really mean that. And then you do need to know the differentiation that I mentioned. After differentiation, you have the flooding, cratering, and slow surface evolution. Those steps in planet formation, which should be they should have been somewhere here. Well, I don't know where they are. I haven't been following and reading this as I've been lecturing about the review. So you should know those states. The Earth, we studied the Earth a lot more than any of the other planets because we use the Earth as our guide to interpret what we see on other planets. So we talked about the Earth's magnetic field. What creates it? Molten core, conducting material that's swirling and has convection. So you need conductive material, swirling, convection. Swirling means go around like this, in case people are not following my language. So if you have any one of those missing, you don't have the magnetic field. Now, jumping from Earth all the way out to Jupiter, Jupiter has a magnetic field. That means it must have those three things. conducting material swirling with convection. But we don't believe that it has a metallic swirling core making its magnetic field. What do we think is making it? Actually, I said metallic. I should have said we don't believe it has an iron.
Liquid.
Because, yes, it's liquid metallic hydrogen. It's hydrogen in a state that is contentious if it's ever been created on Earth. People have claims to create on Earth, but other people say, I don't believe you, because it's so hard to make it. So we believe that you have the conditions necessary, the high pressure, to turn hydrogen into a metal that's conducting but is still liquid. Now you might think, but metals aren't liquid. And of course, mercury is a metal that is liquid at room temperature. So you're actually not that unfamiliar with liquid metals. But you just kind of forget that that's a metal. And that if I take iron and melt it, it's still a metal and it still is conducting electricity. Okay, so we have magnetic field caused by something different. Now let's go further out. Uranus and Neptune. What creates the magnetic fields of Uranus and Neptune?
Weird off-center thing.
Weird off-center thing. More specifically, what material is believed to be swirling around?
It was,
Yeah, a briny, salty water. Now, salty doesn't mean just sodium chloride. There's lots of different salts out there. Like sodium nitrate and whatnot. But it's believed to be a salty, swirling material with maybe some rocks of ice in there that causes turbulence and makes it have its really wicked, weird magnetic fields. What's wicked weird about the magnetic fields of Uranus and Neptune?
it's very, very off-center.
Okay, off-center, like here's the planet and its magnetic field behaves like there's a bar magnet there.
But they move also.
And then they shift around. And they don't point at all toward the poles. Very shifty. Huh. Yeah, that was funny. I'm going to bed soon. Okay, so we talked about the magnetic field caused by the core. We go out, the Earth has the mantle, then it has the crust, and poking through the crust occasionally we have things like volcanoes. And we have two kinds of volcanoes on Earth. One kind that forms the Ring of Fire. Y'all know the Ring of Fire, right? Because we know the song, and it burns, burns, burns. Yes, that Ring of Fire. I have to fight just to not sing.
You can do it.
So, the Ring of Fire is volcanoes that are caused by the mid-ocean ridge having magma coming up, pushing the plates apart. And then those plates, when they hit continental plates, because continental plates are less dense, continental plates float on top of the ocean. And so you have subduction, sliding underneath. But when you have rock sliding on rock, there's a lot of grinding. And grinding makes things hot. And so it melts rock, and that's what causes the volcanoes all around the Ring of Fire. So it's not hard to find the edges of the tectonic plates here. You just look for the volcanoes. That's one kind of volcano. But then there's another kind of volcano. The kind that the Hawaiian Islands are made out of. That is where you have magma that's coming up through the mantle and through the crust to make a volcano. So that's magma from deep, not from grinding, but from deep, pushing up. Now the magma that's coming up and pushing the oceans apart is coming the same way. And so it makes a different shaped kind of volcano. The Hawaiian Islands are called shield volcanoes because they're shaped more like a shield rather than a cinder cone. Why do we talk about that? Because we have other volcanoes in the solar system. Olympus Mons, the biggest mountain in the solar system. Where do I find Olympus Mons? Mars. What kind of volcano is Olympus Mons?
Unactive.
Inactive. Okay, dormant. That works for me.
It's a non-tectonic plate one.
Okay, it's a non-tectonic plate one. It's a shield volcano. It's one where you just have magma coming up from deep. we have evidence that Mars must have a very strong crust because Olympus Mons is not sinking, whereas the heaviest mountain on Earth, Mauna Kea, is sinking under its weight. So that it has a moat. If you were going along the ocean floor, you go down and then up the mountain because the mountain's sinking. So we look at these, the volcanoes on Earth, compare them to other planets to see what's going on there. The Grand Canyon. We have a Grand Canyon on Earth. It's great. It's out there in Arizona. Probably been there. It's not the biggest canyon in the solar system.
The ones on Mars.
The one on Mars again. It's the biggest canyon. We have Valles Marineris. Hopefully I say that right.
Is that name going to be an exam?
Huh?
Is that name going to be?
It could be. Now remember, they're multiple choice or true and false, so it's not like you have to pull it out of thin air, but you'd have to recognize it. And so it's a much bigger, deeper, longer canyon than the Grand Canyon, probably caused by tectonic action in the long, long ago, which, unlike South Park, does not mean a week ago. I don't know if you guys seen that episode, but it's pretty funny. You mean the long, long ago? For people who haven't seen the episode, it's the one where all the kids claim that their parents were molesting them so that their parents would make them do chores. And then you have a society run by children, and it quickly devolves into a Lord of the Flies type situation. And yeah, it turns out the long, long ago was like a week ago. Okay, so back to talking about astronomy. So we have these tectonic things. Now, one of the really interesting things that we had just last class period, which happens to be yesterday, on Ceres, there are big gashes that are longer than the Grand Canyon. So even Ceres has a type of canyon that's longer than ours. But it's not like the Grand Canyon. What created the Grand Canyon on Earth? We believe it was erosion. Now I say we believe it was erosion. It doesn't matter if you are a straight scientist who denies the flood or if you believe in the flood. Both groups believe that erosion is what created the Grand Canyon. The difference is the time that it took for the erosion. Creationists who believe in a young Earth believe that as the flood waters were receding, you had massive erosion that caused the Grand Canyon. And conventional geology says the Grand Canyon was created over millions of years. So they both agree it was the action of water. The question is, was it a lot of water in a short time or a small amount of water over a very large period of time? So we have the Grand Canyon is created by erosion. Valles Marineris, most likely by tectonic action. We do have the, what's it called? What is the?
Trench?
Yes.
Mariana's
Marianas,
Trench.
there it is. The Marianas Trench that I believe is a tectonic created plate. Yes, Otter. Deepest. Then we have the ones on Ceres that were actually, they're believed to be collision-induced grinding that made those. Okay, going further, the atmosphere. We talked about the Earth's atmosphere. Now, I haven't focused too much on the atmospheres of the other planets. The Earth's atmosphere, we have the troposphere, the stratosphere, the ionosphere. Those are the three that we broke it down into. The troposphere is the low one. And what happens in the troposphere? Well, yeah, we do breathe.
Weather happens in the troposphere.
Weather happens. Yes, thank you. The weather stuff that we talk about, that's primarily troposphere. Up in the stratosphere, you have... What do you have there? Stratosphere.
No, I forgot if that's what you said.
Okay. Yes, in the stratosphere.
It's not where it gets very cold.
It actually gets colder as you go up in the troposphere, and then you get stratosphere. It starts to get warmer again, and then of course eventually gets cold again. I believe in the stratosphere is where you have things like the auroras, and then you go up higher in the ionosphere. You have your ionized material. So,
Which one has the ozone layer in it?
wow, I think it's stratosphere. I didn't review for the test yet. I should have known the answer to that. Let's see, it says right here, ozone layer is in the, it doesn't, well, about 50 kilometers from the Earth's surface, the ozone layer, and that's where you change to the stratosphere.
So it's in between.
So yeah, it's in between according to this textbook, and this textbook didn't go higher than the troposphere. Other planets have their atmospheres. What would you tell me about the atmosphere of Mercury?
Virtually
That's
non-existent.
It's, yeah,
Has none. Now there is some evidence that it might hold on to small amounts of hydrogen for a week or two. That is, the sun is constantly bombarding Mercury. I did say Mercury, right?
yeah.
The sun is constantly bombarding Mercury with its solar wind, which contains a lot of hydrogen atoms. And some of those can get trapped for maybe a week or two. But there's no actual permanent atmosphere. Anything that's there is transient. So Mercury, no atmosphere. Why no atmosphere?
It's too small to hold an atmosphere.
Okay, too small. It doesn't have enough mass because you have to have the escape velocity, the speed something has to get away, greater than the speed of the molecules in the atmosphere if you're going to hold on to them. And if you have a small mass, you can't. Question?
The second thing to that would be it's close enough to the sun to where anything that would be considered, that could potentially be held by its gravity, is moving too fast because of the heat.
Right. That's the other part of the situation. Because it's hot, the molecules are moving faster, which makes them more likely to escape. So it has the worst of both worlds. The molecules are moving fast because it's close to the sun. It gets really hot on the side that's facing the sun, and the escape velocity is low. So even if it can hold on to molecules on the cold side, when they come around, it's the hot side, there you go. So Mercury, no permanent atmosphere. Go out to the next planet, Venus.
Has an atmosphere.
Super thick.
Super thick atmosphere. Rough numbers.
Runaway
Compared to the Earth, how thick is its atmosphere?
3 times.
5 times. 500. That's what
At least you read my facial expressions correctly. Somewhere around 100 times is a rough number. About 100 times heavier atmosphere, 100 times thicker. Not primarily oxygen, primarily, it was methane. It's very caustic environment, very hot environment. Because it has such a heavy atmosphere.
Has a lot of CO2.
Yeah, methane. Or, yes, I said methane instead of carbon. I'd have to go back and check. Yeah. I don't remember the numbers.
So it has methane, but it's not blue.
Methane you must be referring to Neptune and Uranus.
Yeah, it probably is CO2. I feel really bad not remembering numbers. I can only blame it on being late at night.
I had to go to the bathroom and wash my face to stay awake. So.
But, okay, it has a very heavy atmosphere, a very strong greenhouse effect, keeping it very hot. So temperatures on Venus are hotter than temperatures on Mercury. And because it has a planet-wide atmosphere, that atmosphere distributes the heat all around to keep it hot everywhere. So how do we know anything about Mercury? Well, the Russians have indeed landed on the surface. We've also had satellites that have gone around and mapped looking through its atmosphere. The atmosphere is not transparent to visible light, but still radio waves can get through. So we do know what the surface looks like, the surface features. And of course, Venus has almost everything named after females. It has highlands, it has lowlands. It does not have liquid water. It's believed that it has the runaway greenhouse effect because it never got cool enough for liquid water. And so liquid water couldn't capture the carbon dioxide and store it as rock. The theory is that Venus and Earth probably had very similar atmospheres at one time. But Earth cooled and trapped the carbon dioxide. Venus didn't. And it has subsequently lost most of its water. You have a question, Alicia? Okay.
You answered it.
Okay, we go out further and we have Mars. Does Mars have an atmosphere?
Very little.
Very little. Rough numbers, how thick is it compared to Earth?
1%. Yeah.
Like 0.6%. I think it's 0.6.
Is that right?
Yeah, it does. I mean, if you said 0.1%, 0.6%, I would quibble, right? The idea is that it's a small percentage of Earth, not a million, not 10. So it's a small fraction. It's once again mostly carbon dioxide, I believe. It's the same gas. I know that. If it was 100% oxygen, would we be good there to live?
No,
Why not?
barren.
Okay, it's barren.
Water. Not enough oxygen.
Okay, there's no plentiful supply of water for us to drink.
It's
there.
too cold there.
Okay, it gets too cold. Now, its hottest temperatures are warmer than it is right now, by a couple degrees. But its coldest temperatures would freeze us solid. So, yeah, we can't live there. What about breathing? If you're in the place, somewhere where it's 68 Fahrenheit, it's 100% oxygen atmosphere at 0.6% the pressure that we have here on Earth, how do you do?
Majority is carbon dioxide.
No, if this is a
You
hypothetical,
wouldn't be able to breathe.
if it was oxygen.
Too much oxygen.
Yeah, it's too much.
No, if you still way too little oxygen, even if it was 100% oxygen.
It's just the
Because
pressure isn't enough for your
The pressure isn't enough for you to breathe, and even if you were able to effectively pull in and out, there's so little that you'd be pulling in and out that you'd suffocate.
You'd have an asthma attack.
That's exactly. Okay, so what happens when we go to the next planet? Does Jupiter have an atmosphere?
Sure does.
Sure does.
It's hot.
What's the primary gas in its atmosphere? Hydrogen. Okay,
Oh, very
it
nice.
has an atmosphere because, does it have a surface that you would hit if you jumped into Pluto? No. If you jumped into Pluto, gas would get thicker and thicker and thicker, and eventually you'd say, hey, I can swim in this, but you never would have even splashed. You never would have hit an interface where you went from gas to liquid. And if you go deep enough, of course, you hit that liquid metallic hydrogen. Obviously, you're going to be crushed at this point anyway, but
You may as well go for it.
but it's going to hurt.
I'd be here.
Okay. Is there anything else that's important about the Earth? Oh, yes. Weather patterns on the Earth. Why do we have tornadoes and hurricanes? The what? Okay, pressure systems.
Because of the Coriolis effect.
Okay, the rotating part is because of the Coriolis effect. I mean, yes, we have the storms because, pressure systems, you have a high pressure system, a low pressure system coming together. But the reason you get the rotating is the Coriolis effect, and that's what I was shooting for. So we have that Coriolis effect of things moving either from the equator north or from the equator south that causes our cyclonic storms. When we get out to Jupiter, Jupiter's storms tend to go all the way around the planet instead of being cyclonic. Why? Because it doesn't have temperature difference between its north pole and its equator, hence you don't have the pressure differences to drive the storms away from the equator, and thus the storms just go around in big circles. And between those circles, where you have one storm going this way and one storm going this way, well, clearly you are going to get vortices that form because of the gases going out, or winds going opposite direction. And so that's what the Great Red Spot is it's a vortex. It's essentially the same thing as a cyclonic storm, except for it's between these two storms going opposite directions around the planet.
So with that being said, and also with our understanding that there is no splash, meaning it's just this huge gradient of the atmosphere down in the core. How far, just out of curiosity, how far down do these storms reach?
I don't recall. For a random reason, I remember that the Great Red Square goes 50 kilometers up in the air, I think it is. Or, actually, it could have been 90 kilometers. I think it's 50 up. Above the surrounding planet. But, yeah, I don't know. So, belts and zones. The weather patterns on the the Jovian planets, the gas giants, are belt zone patterns. The belts do essentially the same thing as my belt does. There are places where you have a lower pressure, things fall in. The zones are like my belly, higher pressure pushing out. And so the belts tend to be darker because they're lower, maybe more in shadow. There's also some temperature differences. Temperature differences will change the reflectivity and absorption properties of the gases, which, as you've learned, makes a difference to the colors. Saturn has the same belt zone patterns, but it's colder. And because it's colder, it obscures, you can't see as clearly the belts and the zones. So you don't see the nice patterns like you see on Jupiter. Get to Uranus and Neptune. They also have belt zone weather patterns. Okay, the moon. What made the moon?
We believe that it could have been God.
Okay.
We
I believe it could have been God.
Right. We believe from strictly evidence that it could have been an impact.
Okay. And we went through, we had the clicker question, you might recall, with the different theories. And I told you every one of them was a scientifically based theory that had been proposed as to how the moon came about. It's not like you only get one theory thrown out and then examine the predictions of the different theories, and it was determined that the only one that seems to make sense is that there was a large impact between the Earth and another object, maybe something the size of Mars, that broke off a bunch of the Earth. It was orbiting the Earth, came together to form the moon. The moon, we see lots of craters on the moon. Why do we see craters on the moon, not on Earth? Very simple.
No water, no erosion.
Lack of water in atmosphere. Okay, so there's nothing to change the surface. Now, the moon is covered with a regolith, a powdered rock, that's meters deep. How could it have a meters deep powdered rock covering?
From thousands and thousands of impacts.
Yeah, from tiny impacts happening over and over and over again. And so it's basically been sandblasted to get that going on. It doesn't have any wind, so stuff just stays there. Okay, looking at our planets some more, let's just go to comparing the planets and then call it good. So comparing the planets. Which planet is the smallest?
I'm going to say Mercury.
That's because you're right. Which one's the largest?
I'm going to say Jupiter.
Anybody besides? Yeah, there's our answer. He's right on both counts. Which planet has the strongest magnetic field? Jupiter. Which one has the weakest magnetic field?
This is a trick question.
Yes, it is. Well, you have Mars, Mercury, and Venus, all with really small magnetic fields. I think Mars is, well, it's not a planet, so it doesn't count. Mars has, last I read, some regions that have magnetic fields, but no planet-wide magnetic field. Venus is very, very, very weak. And Mercury has a weak magnetic field, but one that's definitely there. So when you look at that, different conclusions for each one. So let's start with Mercury. What's the conclusion scientists have drawn on why Mercury has a very weak but existent magnetic field?
The iron core, it's fitting, so it has a slight dynamo.
Okay, it has an iron core that's freezing but not completely frozen yet. So it still has some dynamo action and some convection. What about Mars?
Solid core.
They believe that it's a solid core that's completely frozen. So now how would Mars, a bigger planet that thus cools more slowly, have a frozen solid core where Mercury doesn't?
Mercury is closer to the sun.
Okay, Mercury's closer to the sun, so it's going to get a lot more solar radiation, which gives it more heat. Also, remember Mercury has a much bigger percentage-wise core than the other planets. So that's going to mean that
Takes a lot.
for other planets of the same size, this would have more iron. It's going to have more heat there, that you have to cool. So it has a couple things that might help explain why it still have a partially molten core.
Talking about Mercury?
Yes, I am. Did I say a different name? Okay. I worry about my brain. It's the truth. Okay, Venus. Why do they believe Venus has virtually no magnetic field? Now, I think our textbook says that, but that is not the party line. That's not the basic scientific understanding. The calculations show that even with its very slow spin, it still, in theory, should have a magnetic field. And so the actual conclusion that is drawn for the mainstream scientists is that it must be lacking convection. It has such a hot surface
That it's just even throughout.
that it doesn't have a big enough temperature difference to cause convections. Now, you get to Jupiter, the strongest magnetic field. Well, that just makes sense. Jupiter and Saturn rotate really quickly, right? Both of them take in the ballpark of 10 hours to do one rotation. And so rotating really quickly, you have that conducting material that's pretty far away from the core, moving really fast. It's very easy to understand how you have a strong magnetic field for those two. They're very strong. They're so strong that their auroras, their northern southern lights, tend to be more ultraviolet than visible light because there's so much energy involved. Then we go out to the last two. We've already talked about the magnetic fields. Yes?
Why is Saturn so much weaker than Jupiter though? Because it doesn't have the same size core, and then Saturn's actually spinning faster. So
Its rotation rate is, faster, but not a lot. 10.7 versus 9 point something.
it's like 9.9.
Yeah. So it's
Why
not
is it so much weaker?
I would surmise that it's based on size. Let's talk about rotations. First of all of the planets are orbiting in nearly the same flat plane. That fits with the idea of the big cloud of gas that then got crushed together, and because it was spinning, flattened out into a plane. The planets are mostly lined up, going around with their rotational axes the same direction as their orbital axes. But there are some notable differences. Let's start with Earth and Mars. What's different about this for Earth and Mars? Earth is tilted 23.5 degrees. How much is Mars tilted? Like 25 degrees. So Mars tilt, let's be honest, 23.5 and 25 is not a big difference. Mars is tilted pretty similarly to us, which means that it would have seasons similar to us if it had, of course, the atmosphere like we have and was the same distance from the sun. It doesn't have our atmosphere, so its seasons are far different simply because you don't have the atmosphere. But you still have a summer season, a winter season, and so it has ice caps that, just like our ice caps, will grow during the winter, shrink during the summer. Its ice caps have liquid water, frozen water, and then covered with dry ice, carbon dioxide. Okay, so those two, what would make them tipped around 23.5 to 25 degrees?
Collision.
Yeah, collisions is our only answer. There is always the hypothesis that maybe we've got it all wrong and they just formed that way. Or, maybe God created them that way. It's not a scientific idea to say God created them that way, but that doesn't make it a wrong idea. So, we have those two. Then let's go to Venus. What's odd about Venus's rotation?
Spins backward or counterclockwise.
Retrograde.
It spins backward. Very, very slowly.
So,
What would cause that?
collision.
Collisions! Okay, what about Mercury? What's odd about its orbit?
It's oval orbit.
Okay, it's more elliptical and its rotation is locked into that 3-2 resonance that we talked about. So it does, in the time of 2 orbits, it does 3 rotations, and thus you have 1 day. So 3 rotations, 2 orbits, 1 day. Very odd. Why? Not collisions. Why?
Oh, its orbit is so close to the sun.
Yeah.
It's very elliptical. That's most of what I remember right now. But something about that, how close it is, the gravity pull on it is slow to temper.
Okay.
Good job,
He's
Zoe.
very close to the full story.
You got it.
Because it's so close to sun, gravity is really strong. And the fact is, nothing is perfectly symmetrical. And so the side of the moon, or of Mercury that is slightly more dense, is pulled much more strongly to the sun. And so it's tried to lock in, like the moon is tightly locked to us, so we always look at the same side of the moon. Mercury tried to lock in, but it can't because it's elliptical in its orbit. It goes faster when it's close to the sun and slower when it's farther away. Whereas the rotation needs to be constant rate. And so what it's done is it's found a resonance between its orbit and its rotation. The moon, because it's much closer to a circular orbit, was able to lock in so one side is always facing the Earth. And remember, as a result of that, the core of the moon is actually offset toward the Earth. The moon's core is closer to us. Well, closer to the side of the moon that we see than it is to the other side of the moon, the side we never see. And the moon is not perfectly circular orbit, so it has its libration. It looks kind of like it wobbles in its orbit when you look at it, take pictures every night, because it's going at a constant rotational rate, but its speed is speeding up a little, slowing down. Okay, the last one that has some weird rotation is Uranus. And why is Uranus weird? Yes, because it's tipped over roughly, it's what, 98 degrees? It's pretty close to 9 degrees, so it's basically on its side as it goes around. So there will be times of the year when the pole is facing the sun, times of the year when the other pole is facing the sun, times of the year when the equator is facing the sun. It has an 84-year orbit, and so you would be like half of that 84 years sunlight if you're on a pole. Half of the 84 years, no sunlight if you're on the pole. You would have the most extreme weather possible on Uranus. Wow. Clearly, my tablet decided that was enough review.
Your tablet's done.
I think it's close, but we haven't talked about the asteroids yet.
Let's do it.
Asteroids. Where did they come from?
Asteroids.
No, that's where they are, where they come from.
Oh.
Not to yours, son.
The collisions of the planets.
Okay, a collision between protoplanets.
Oh.
And Mars?
No, between protoplanets probably.
Oh.
You have to have had a differentiated protoplanet get hit, or planetesimal, like I said. I'm not going to hold you, I can't remember which one's which. But you had to have something that's already differentiated and then got a collision, broke apart. Why already differentiated? Well, Holly, clearly we've gone through this. Already differentiated. Why do we know they're already differentiated?
Because
Because there's different, like they have different compositions.
Because we have some asteroids that are like iron, some that are like rock. We have different compositions, which means that if it all came from one thing, they had to differentiate. Now, Ceres, it was proposed, may be a pristine protoplanet. Okay, so asteroids. Most asteroids are in the asteroid belt between Mars and Jupiter. There are some that are closer, so the Earth shares orbit with some asteroids. And I think it was Eliezer that asked about, clearing the orbit. There are the Trojan asteroids that orbit with Jupiter. Was that going to take away Jupiter's planethood? No. Because the mass of the entire asteroid belt is just a fraction of a planetary mass. In fact, remember, Ceres, that is something times 10 to the 20 kilograms is 1/3 of all of the mass in the asteroid belt. Yeah, there's not that much mass out there. And so it doesn't interfere with anything claiming planethood. Now that somebody has mentioned the Oort cloud, I remember a first thing we should have talked about, things in the solar system. Clearly, the first thing is the sun, our star. And then we have our planets, our 8 planets, the dwarf planets, the 5 dwarf planets, the asteroids, and then we have to take into account 2 more things, the Kuiper belt and the Oort cloud. The Kuiper belt is essentially these icy objects that are in the flat plane of the solar system that extend beyond Neptune out, 100 astronomical units or so away. The Oort cloud is a spherical cloud of the same type of icy objects that is like 1,000 astronomical units away. And when we talk about comets, which will be next week, we'll learn that comets come from those 2 things, either the Kuiper belt or the Oort cloud.
What's the difference between comets and asteroids?
The difference is, it's a very clear-cut difference. Asteroids are solid objects that are rock or iron. Comets are icy objects. So it's, one could say, well, the asteroids are probably formed inside of the frost line, the comets outside the frost line. In fact, the comets have some rock in them too, but they have all the icy things because they're formed out there where things could collect ice. And so that's the big difference, ice. Okay, I think now that covers my review. For the exam, it'll be very similar in number of questions to the last exam. Once again, all multiple choice or true and false, except for the one question that you know is coming. Please, don't get the order of the planets wrong or the names of the planets wrong. I know probably half of you knew all of that before you even took the class. It seems every year there are 2 or 3 students who don't get it straight. And it baffles me because I told you it's going to be there.
So we have to know something about them though, too.
Yeah, you have to know something about them. Obviously, that's something you can't know exactly what's going to be.
It can just be simple, like, oh, it's an ice planet or an ice giant, or do you,
Well, I will specify the category. So, like I said, the example of, which ones have 0 moons, 1 moons, 2 moons, or more than 2 moons. Or, which ones have a magnetic field, which ones have an atmosphere, that kind of,
Okay.
So I'll specify what it is. So you can't just say, well, I know that this one has this many moons. If I didn't ask you about the moons, I won't.
So you're gonna
Yeah, I'm going to specify
ask
what
them
you want to
questions,
know
so you
about
just
it.
have to know about all. Okay.
Yes. Caleb,
What are the units?
the units of?
The chapter.
Oh, the test is going to be covered.
Yeah.
Okay, what was it? 25 or 26 was the starting point?
25,
So everything says solar
I-
system.
Hmm?
Everything that says solar system.
And, well, it's supposed to be everything that says solar system, except we didn't get to talking about comets. And, we didn't get to talking about comets. And so, let me see the textbook. I will tell you where we cut off. Because it's better to know a number and know, okay, there will be no questions beyond here. Okay. There will be no questions about the moons of Jupiter and out. And there will be no questions about the rings. And nothing from, so basically it'll be out to, out to 46.
25 is 40, 46. 25 and 46.
I think that's right, but I'm going back and I'm going to check the other end as well. Well, no, not 25. We're not gonna do any relativity, so no 26 or 27 for sure. Yeah, so it would start at 28. So did everybody hear that? 28 to 46. Okay. And
Are you gonna post the recording?
yes, I'll post the recording. Actually, it fell asleep. I don't know if it's still recording. We'll see.
Basically, the exam will cover from